Let us discuss nucleophilic substitution reactions. Nucleophilic substitution reactions. Okay, we'll take alkyl halide, for example, ethyl bromide. It is reacting with aqueous potassium hydroxide. Aqueous potassium hydroxide. What is the product here? Ethanol and KBr. Ethanol and KBr. Now, ethyl bromide. Ethyl bromide we can write like this. Ethyl bromide we are writing like this. Potassium hydroxide we can write like this. Potassium hydroxide we have written like this. Then this hydroxide O is attacking this carbon, this bond is shifting. Therefore, Br minus is the leaving group, OH minus is the nucleophile. Okay, so in this case, what is the nucleophile? Nucleophile is OH minus. Leaving group is Br minus. Leaving group what in the sense Br minus we can say. Next, with moist silver oxide, reaction with the moist silver oxide we will see. Reaction with the moist silver oxide. Moist silver oxide in the sense silver oxide plus water. Silver oxide we can write it as like this. Water we can write it as like this. Therefore, what we are getting in the sense AgOH we are getting AgOH. So now this alkyl halide with the moist silver oxide. This alkyl halide with the moist silver oxide, what is possible that we'll see. So alkyl halide we will take it as a ethyl bromide. Moist silver oxide will take silver. Moist silver oxide means silver hydroxide. Now, what is the product that we will see? Here, nucleophile is OH minus. Leaving group is Br minus. Leaving group is Br minus. Therefore, what we are getting in the sense C2H5OH we are getting and AgBr we are getting. Set. So, alkyl halide with moist silver oxide we are getting a alcohol. Nucleophile is what in the sense OH minus. Okay. Next reaction we'll see. This alkyl halide with alkoxide we will take. With alkoxide. Alkoxide in the sense sodium alkoxide or potassium alkoxide we will take. Alkoxide. Alkoxide means RO minus K plus. Alkoxide we have taken. Alkoxide. Here, what is the nucleophile? Nucleophile is alkoxide. Nucleophile is what means alkoxide. Therefore, we will get ROC2H5. Br minus is the leaving group, that is leaving. Set. So we got alkoxide in the sense nucleophile is alkoxide. Then we will treat with KCN and AgCN. Set. With KCN, what is the reaction? We will see. It is alkyl halide. KCN we will take. KCN in the sense this cyanide we will give like this. Cyanide we can give like this. Cyanide we can give like this. So it is a nucleophilic center. It is a nucleophilic center. Therefore, we will get RCN. Okay. Now we will see with AgCN. We will see alkyl halide with AgCN. We will see AgCN. We will write it as AgCN like this. We will write. It is a nucleophilic center. That N is a nucleophilic center in this case. Therefore, we will get R and C. Isocyanide we will get. So, in cyanide, in potassium cyanide, if we take carbon is the nucleophilic center, therefore cyanide we compound will get. AgCN if we take N is the nucleophilic center, isocyanide we will get. Then we will see. Then we will take a silver nitrate. alkyl halide with AgNO2, silver nitrate we will take. Silver nitrate in the sense we can write this is like this. We can write like this. Here, which one is the nucleophilic center in the sense this is the nucleophilic center. It is a nucleophilic center. So, what is the compound we will get in the sense we will get the compound like this. We will get like this compound. Nitro compound we will get. Sir. Now, alkyl halide will take KNO2 will take KNO2. So, what we will get you will see K plus NO2 minus that we will take. Here, which is a nucleophilic center in the sense this oxygen is the nucleophilic center. This oxygen is the nucleophilic center. So what we will get in the sense we will get this compound. So we will get to what compound in the sense a nitrite we will get. Here nucleophilic center is this oxygen. Okay. So NO2 minus is the nucleophile. This oxygen is the nucleophilic center. Oxygen is the nucleophilic center. Therefore we will get alkyl nitrite we will get. We will get alkyl nitrite we will get. Sir. Next alkyl halide with alcoholic ammonia we will see. Alkyl halide with alcoholic ammonia. Alcoholic ammonia we will see. Alkyl halide with alcoholic ammonia. What is the reaction we will see. Now this RBr will take, ammonia will take, ammonia, this is having lone pair. So this is attacking this Br is leaving, therefore it is nucleophile. So which is nucleophile? Nucleophilic center means this N. N is the nucleophilic center. So we are getting a RNH3 plus. So from this H plus is leaving, therefore we will get RNH2. Okay, this RNH2 react with RBr in the sense one hydrogen is replaced by R, therefore RNHR will get. Again RBr in the sense this H is replaced by R, therefore we'll get so and so will get. Again RBr in the sense. So how the reaction will be there? In the sense this nitrogen is having lone pair, this lone pair will attack, this Br minus is leaving, therefore we will get R4N plus. R4N plus will get this plus charge is balanced by this Br minus. So we are getting so and so. Next reaction we'll see. Now alkyl halide we are taking. Then potassium hydrogen sulfide we will take. Potassium hydrogen sulfide. In this one, which is the nucleophilic center, that we'll see sulfur is having 3 lone pairs. It is a nucleophilic center. That sulfur is the nucleophilic center. So we will get so and so compound. This is what in the sense thiol, thioalcohol or thiol we can say. One example we will take in the place of R we will take C2H5. So C2H5SH we will take. What is the name of this compound that we'll see? C2H5 we will call it as ethyl. SH is called thioalcohol. Suppose here OH is there means alcohol we will say no. Instead of O, sulfur is there, therefore thioalcohol we are saying. Sir, another name. This ethyl we will write as it is. SH we can write it as mercaptan. SH we can write it as mercaptan. SH is mercaptan. Next, another name we will see. Here 2 carbon atoms are there. 2 carbon atoms means root word is eth. Then primary suffix. Primary suffix carbon single bond is there. Therefore ene. For this SH, what is the secondary suffix? Thiol. Therefore ethane thiol. This E we should not remove because this T is not a vowel sound. So don't remove this E. Ethane thiol is the IUPAC name for this compound. Sir. Next we will take this alkyl halide we will take. Then we will take a so and so compound we will take. So and so compound will take. So what we will get? That we will see. Here mercaptide ion we have taken. We have taken mercaptide ion. This RS minus. This RS minus is called what in the sense? Mercaptide ion. Mercaptide ion we have taken. Which is a nucleophilic center means this is the nucleophilic center. That is a nucleophilic center. So what we will get in the sense RSR, it is called thioether. Thioether we can say. In the place of S, if O is there, that is called ether. S is there, therefore thioether we can say. So we are getting a thioether we can say. Sir, next we will take a alkyl halide will take. We are taking alkyl halide. Then we will take a sodium sulfide will take. We are taking sodium sulfide. This sulfide is having 4 lone pairs. So how the reaction is there, you see, this lone pair attacks this R, Br minus is leaving. This lone pair attacks this R, Br minus is leaving. So what we will get in the sense RSR. This is called what in the sense? Thioether. This is called thioether we can say. We are getting thioether, we are getting. Sir, okay. Next we will see, next reaction. Alkyl halide will take alkyl halide. Then silver acetate will take. Carboxylate and carboxylate substance will take. Carboxylate. Silver salt of carboxylic acid. Silver salt of carboxylic acid we have taken. So what is the reaction? We'll see. Here this oxygen attacks this R. This is leaving. So this bond is migrating. So this Ag plus and X minus becomes AgX. So what we will get in the sense this carboxylate ester. We are getting ester is the compound here. We are getting ester. Okay, so we got ester. Therefore, nucleophilic center is this O. Nucleophilic center is this O. Next, we will take alkyl halide. Then we are taking a reducing agent lithium aluminum hydride. We will take reducing agent lithium aluminum hydride. We will take. So, what is the product we are getting? Means ethane is the product. So, how we are getting that? We will see. Ethyl bromide. We will write. We are writing ethyl bromide. This lithium aluminum hydride, we can write it as Li plus AlH4 minus. AlH4 minus we have written. So what happens means this hydrogen takes this bond and attacks this carbon. Br minus is leaving. Therefore, we are getting a C2H6. Okay. So next reaction we'll see. Now we will take a nucleophile is this one. CH minus COOET COOET like this we will take. Alkyl halide will take or Br will take. So what will happen means this C minus will attack, this will leave. Therefore, we have R will be introduced. R will be bonding with this carbon. R will be bonding with this carbon, we can say. So this is about nucleophilic substitution reactions of alkyl halides. Nucleophilic substitution reactions of alkyl halides, we can say. So next we'll see about aryl halides chemical properties. We'll see aryl halides chemical properties. We'll see aryl halides chemical properties. Okay, so for alkyl halides chemical properties we have seen. Now we will see aryl halides chemical properties. Aryl halides chemical properties. Okay, now aryl halides with the nucleophilic substitution reaction we'll see. Now we'll take first ethyl halide, ethyl bromide will take. We'll treat this with sodium hydroxide aqueous. What will happen means OH minus is the nucleophile, OH minus is the nucleophile, Br minus is the leaving group. Therefore, we will get ethanol is the product. It is for alkyl halide. Now we will take aryl halide. Aryl halide, what in the sense? Chlorobenzene will take. It is aryl halide. It is alkyl halide. Okay. Now we will treat this with the sodium hydroxide aqueous. What is the reaction? Means no reaction for this. For this, no reaction. Sir, why no reaction in the sense? Between this here, in this place, between carbon and chlorine, what is there means partial double bond is there due to resonance. Partial double bond is there due to resonance shown by this Cl. Resonance shown by Cl. Resonance Cl is showing plus R effect, benzene is showing minus R effect. Therefore, between CCl, partial double bond is there. Therefore, this nucleophile is unable to replace this leaving group. Okay, this nucleophile is unable to replace this leaving group. Therefore, it is not going for nucleophilic substitution reaction. Sir, now we will take a. Now we will take vinyl chloride. Will take CH2 double bond CHCl. Vinyl chloride will take. We have taken a what in the sense vinyl chloride. Vinyl chloride with the sodium hydroxide. What is the reaction? Sodium hydroxide aqueous. No reaction. So why vinyl chloride is not reacting with the sodium hydroxide aqueous? That we'll see. In the vinyl chloride, what is possible in the sense resonance is possible. Mesomeric effect is possible. That means this lone pair is becoming pi bond. This pi bond becomes a lone pair. So due to this mesomeric effect, what happens means CH2 becomes a negative charge, single bond CH, double bond Cl. Cl is getting positive charge. So because of therefore in this between this CCl, between the C and Cl, partial double bond is there in the resonance hybrid because of resonance. Therefore, here also what is happening means this Cl is not replaced by this OH minus. So nucleophilic substitution is not possible, sir. So nucleophilic substitution reaction is possible here, not possible here, not possible here, we said. Okay. Here using partial double bond. Using partial double bond, we said regarding this. And another point we will see using hybridization. Using hybridization, we'll see. Now, ethyl bromide will take. Ethyl bromide. Ethyl bromide and this bromobenzene will take. Now we will see regarding hybridization. This is sp3 hybridization, whereas it is sp2 hybridization. sp2 hybridization means electronegativity is more, sp3 hybridization means electronegativity is less. So this is less electronegative, whereas this carbon is more electronegative. This carbon is more electronegative, therefore it is attracting Cl strongly when compared to this carbon. So that breaking this bond is difficult, breaking this bond is easy. Therefore, it is not going for nucleophilic substitution reaction, whereas it is going for nucleophilic substitution reaction. Sir. Next. Now, this chlorobenzene will take. This chlorobenzene is not going for nucleophilic substitution reaction under normal condition. Sir. Now we have taken chlorobenzene. We have added sodium hydroxide aqueous. What is the reaction? Means no reaction. Reaction is not taking place. So we will do one thing. We will keep high temperature. We will provide high pressure. We are providing high pressure. We have taken chlorobenzene. We have added sodium hydroxide aqueous into this. We are providing high temperature and high pressure. 300 atmosphere in the sense huge pressure we are providing. So what will happen? Due to high temperature and huge pressure, what happens means this Cl minus is replaced by what in the sense OH minus. So we will get like this. This it is Na plus OH minus. OH minus replaces Cl minus. because we have given a abnormal condition. Very huge pressure we have given, high temperature we have given, so that it is happening. Then this phenol is reacting with the sodium hydroxide. This H plus is taking this OH minus and becomes water. Therefore, we got a sodium phenoxide. We are getting what in the sense? Sodium phenoxide we are getting. It is called acid-base reaction. Phenols can react with the sodium hydroxide. It is an acid, it is a base. Sir. Then it is treated with HCl. Now Na plus and H plus are replaced. Therefore, we are getting what in the sense? Phenol we are getting. Okay. So chlorobenzene with the sodium hydroxide aqueous gives phenol. That means nucleophilic substitution reaction is possible because we have given a very huge pressure and high temperature we have given. Therefore, nucleophilic substitution reaction, we made them to undergo nucleophilic substitution cell. Next reaction we'll see. Now we will introduce one nitro group here. One nitro group we will introduce into this phenyl ring. What will happen? We'll see. Now we will take we are introducing one nitro group. One nitro group we have introduced. Now we will add aqueous solution of sodium hydroxide. So what happens in the sense? We are providing what condition in the sense 443 Kelvin we are providing. So Cl is replaced by OH. That OH is reacting with the sodium hydroxide. Therefore, we are getting phenoxide. Then it is treated with the dilute HCl. So O minus becomes OH. Okay. So here you see that we are providing just less temperature when compared to this, but reaction is taking place. Pressure we are not giving. Why? What is the reason? That is due to NO2 group. So in what way this NO2 group? Due to this NO2 group, reaction is possible at less temperature and normal pressure. Here NO2 group is not there. Huge pressure is required for nucleophilic substitution. Here because of NO2, this reaction, this nucleophilic substitution reaction requires no pressure, normal pressure is required. Less temperature is required. What is the reason? Why like this happened? That we will see. Now we'll take this para nitrochlorobenzene will take like this we have taken. Here resonance is possible. Here what is possible in the sense resonance? This bond is migrating to this side. Therefore, we will get what in the sense here N is getting 2 plus, O is getting minus charge. We will give pi bonds. Okay. It is one resonance structure. Next, this pi bond is migrating to this place. Now, here double bond, N is having plus, O minus, here positive charge, here pi bonds. Okay, next resonance structure we'll see. This pi bond is shifting to this place. This pi bond is shifting to this place. Therefore, we will get here pi bond, here positive charge. Okay. So next resonance structure we will see. This pi bond shifted to this place. Now we can write pi bonds like this, positive charge here. So this NO2 group is acting as a electron withdrawing group. Because of this electron withdrawing group, this position is getting positive charge. This carbon is getting positive charge. This carbon is getting positive charge. Okay. So that this NO2 group, with respect to this, ortho carbon gets positive charge. With respect to this, para carbon gets positive charge. With respect to this, ortho carbon gets positive charge. So NO2 group, due to NO2 group, with respect to that, ortho and para carbons getting positive charges because NO2 group is electron withdrawing group. So this NO2 group creates positive charge at this carbon. This carbon is therefore this NO2 group makes this carbon to get higher electron deficient. So OH minus can easily attack this electron deficient carbon. Here positive charge is there. Therefore OH minus is easily attacking. Therefore this nucleophilic substitution reaction requires less temperature and normal pressure. Let us introduce one more electron withdrawing group. What will happen? We'll see. We will introduce one more electron withdrawing group. Okay, so here one NO2 group, here one NO2 group. Now we will add a sodium hydroxide aqueous. We are adding sodium hydroxide aqueous. What is the condition required in the sense 368 Kelvin we have to provide. Then this Cl becomes O minus Na plus. Therefore, we will treat with the dilute HCl. So Cl minus will be replaced by OH now. Okay, so here NO2 group, here NO2 group. In this case, you see that temperature required for this nucleophilic substitution is still less than this above, because 2 electron withdrawing groups is there. This electron withdrawing group creates positive charge at this carbon. This electron withdrawing group creates positive charge at this carbon. So both electron withdrawing groups create positive charge at this carbon. Therefore, this carbon is having higher electropositive. This carbon is having higher positive charge when compared to this carbon. Therefore, this reaction requires less temperature in order to take place. Sir, next we will see. Next reaction we will see. We will introduce one more electron withdrawing group. We will introduce one more electron withdrawing group. Here one electron withdrawing group. Here one electron withdrawing group. Here one electron withdrawing group. Okay. Now just add water and warm. You need not add sodium hydroxide. Just add water and warm. What will happen means Cl is replaced by OH. So here we will write NO2 group. Here NO2 group. Here also NO2 group. Now see that nucleophilic substitution is possible with water. But in this cases, nucleophilic substitution reaction is possible with sodium hydroxide. Sodium hydroxide is giving better nucleophile OH minus. Water is a poor nucleophile when compared to OH minus. Sodium hydroxide is providing better nucleophile, that is OH minus. Water is not providing better nucleophile. It is weak nucleophile only. Therefore, though weak nucleophile is there, the reaction is taking place because of 3 electron withdrawing groups. All the 3 electron withdrawing groups create positive charge here. Therefore, this carbon is having high electron deficient when compared to other carbons. Therefore, here even water itself attacking this place. Water itself attacking this place. Generally, organic compounds do not dissolve in water, but water is attacking here and nucleophilic substitution is possible here. Because of what? 3 electron withdrawing groups. 3 NO2 groups act as electron withdrawing groups. Therefore, here reaction is possible. Sir. Next nucleophilic substitution reaction we'll see. We'll take a bromobenzene. Cuprous cyanide will take in the anhydrous form. Cuprous cyanide anhydrous. Then we will keep a pyridine. Otherwise a dimethyl formamide. We are taking dimethyl formamide. Then we are providing temperature 470 Kelvin. So what we are getting in the sense cyanobenzene we are getting cyanobenzene. Okay, so this Cn, this Br minus is replaced by Cn minus. This Br minus is replaced by Cn minus. So aryl halide, anhydrous cuprous cyanide, pyridine or dimethyl formamide we are taking 470 Kelvin. So what we are getting in the sense cyanobenzene we got cyanobenzene. Okay, next reaction we'll see. We'll take chlorobenzene. To this we will add ammonia we will add, and cuprous oxide catalyst we will add. We are adding. we are providing 475 Kelvin temperature and 60 atmosphere pressure. 60 atmosphere pressure. What is the compound obtained? In the sense aniline is obtained. Aniline is obtained. Aniline is the compound obtained here. Okay, so chlorobenzene with ammonia gives a aniline set. So this is undergoing nucleophilic substitution. In the sense, what is the mechanism involved here? Okay, what is the mechanism involved here? That we'll see. In which, using which mechanism this is explained. This explained. Okay, so nucleophilic now mechanism of nucleophilic aromatic substitution reactions. Okay, mechanism of nucleophilic aromatic substitution. So one is what in the sense addition elimination mechanism. Addition elimination mechanism. Addition elimination mechanism or SNER mechanism. SNER mechanism or direct displacement. Direct displacement. Next one is elimination addition mechanism. Elimination addition mechanism, otherwise benzene mechanism. Benzene mechanism. Okay, so nucleophilic aromatic substitution. Aryl halides undergoing nucleophilic substitution reaction. For that, two mechanisms are there. One is addition elimination mechanism. Another one is elimination addition mechanism. Sir, first we will see addition elimination mechanism. We'll see. So first we are taking addition elimination mechanism. Addition elimination mechanism we'll take. Okay. Now for this first step, what in the sense we'll take chlorobenzene. Chlorobenzene we have taken. Nucleophile is attacking. Nucleophile is attacking this chlorobenzene. Okay, nucleophile is attacking this carbon. This bond is shifting here. Okay, therefore we are getting what we will see here: chlorine, here nucleophile, here what in the sense a negative charge, here pi bonds. It is going for resonance. It is going for resonance. A negative charge becomes pi bond becomes a negative charge. So here pi bond is there, here negative charge is there. Okay. Next we will see this negative charge becomes pi bond. This pi bond becomes a negative charge. Cl, here nucleophile. Now here pi bond, here negative charge. Okay, so on, so resonance is possible. Sir, we'll see next step. Next step we will see here Cl, here nucleophile. Now pi bonding electron cloud is distributed here. Negative charge here is present. Now what is happening means Cl minus is leaving. Now what is happening when Cl minus is leaving? So for which we will take one of the resonance structure we will take instead of taking resonance hybrid. One of the resonance structure we are taking, that is here negative charge we will take. This negative charge becomes pi bond. The Cl takes this bond and becomes Cl minus and leaves. So nucleophile is made bond with the carbon. Here pi bonds will give. Cl minus left. Here Cl minus is leaving, therefore elimination it is. Here nucleophile is adding, therefore it is addition. Here nucleophile adding in the sense, already this phenyl ring, is a electron rich center. Why electron rich center? In the sense, instead of saying electron rich center, we can say delocalized pi electron cloud, we can say. Because of delocalized pi electron cloud, it will repel nucleophile to attack. Even then nucleophile attacking means how this step will be there? It will be slow step. Here Cl minus is leaving, therefore we are getting like this compound, therefore it is fast step. Okay, therefore it is a slow step, it is fast step, we can say. This is called addition elimination mechanism. First addition is possible, then elimination is possible. Okay, now you say that if phenyl ring is having electron withdrawing group, then attack of nucleophile will be made easy. Okay, so now we will take a aryl iodide, aryl bromide, aryl chloride, aryl fluoride. What about rate of nucleophilic substitution? That means which leaving group is better leaving group here? Which leaving group is better? High. Therefore, rate of nucleophilic substitution reaction will be like this. Rate of nucleophilic substitution reaction is so and so in this case. Sorry, okay. We'll see next elimination addition mechanism, that is called benzene mechanism. We'll take benzene mechanism. We'll take benzene mechanism. Benzene mechanism we'll take. Okay. Now for this we'll take an example. We'll take chlorobenzene. We'll take chlorobenzene. To this we are adding NaNH2 sodamide. NaNH2 is called sodamide. This is dissolved in what? In the sense liquor ammonia. In liquor ammonia. It is dissolved in liquor ammonia. So what we will get in the sense aminobenzene we will get. We will get aminobenzene. We have got what? In the sense aminobenzene we got. Okay. So what is the reaction? What is the mechanism possible in this case? That we will see. Now we will take this chlorobenzene. Here chlorobenzene we are taking. Now this from this NaNH2, NH2 minus comes. This NH2 minus comes. This NH2 minus, it is abstracting proton. It is abstracting proton. This sigma bond becomes lone pair. Sigma bond becomes lone pair. Therefore, we will get here pi bonds will give. Here lone pair will give negative charge. We are giving here Cl is there. Okay. This NH2 minus is a strong base. It takes H plus and becomes ammonia. Next step. What happens? Next step, what happens? That we'll see. This lone pair becomes pi bond. This bond is leaving. Therefore, Cl minus leaves. Now what happens means Cl minus is leaving. So we'll get like this. We got like this. Sorry. Now, shall we call this as a triple bond? No. Why it is not triple bond means these three pi bonds are in delocalized pi electron cloud. This pi bond is perpendicular to these three pi bonds. This pi bond is perpendicular to these three pi bonds. Therefore, like this it is there. Okay. Now, this is called what in the sense benzene. It is called benzene. Now, this NH2 minus again comes. This NH2 minus again comes and attack. So, how the NH2 minus will attack? That we'll see. If NH2 minus attack this carbon, then this pi bond will shift to this carbon. So we will get here delocalized pi electron cloud we have given inside the ring. Here NH2, here negative charge. Then this negative charge abstract proton from this ammonia. This negative charge abstract proton from this ammonia and becomes like this. And becomes like this. It is providing, it provides H plus to this and becomes NH2 minus and leaves. Set. Next possibility we'll see now. We'll see about next possibility. If NH2 minus attack this carbon, then this pi bond will shift it as negative charge. This carbon gets a negative charge. It takes H plus from ammonia and becomes a CH. So we got what in the sense aminobenzene, here also aminobenzene. This one and this one remain same, isn't it? This one and this one remain same. Then what is the necessity of saying that this NH2 minus can attack here or here? Sir, to understand that, let us label this. Labeling means C14 carbon. It is C14 carbon. We have labeled this. So it is C14 carbon. It is C14 carbon. Now you say this one and this one are the same? No. Therefore, NH2 minus can attack this carbon, otherwise this carbon it can attack. Okay. Now, in this case, if you see, first this NH2 minus abstracting proton and becoming ammonia. Therefore, it is elimination. Elimination of proton here. Here NH2 minus is adding. Therefore, it is addition. It is addition. So, elimination addition mechanism it is. First elimination followed by addition. This is called benzene mechanism because intermediate is benzene. This benzene mechanism is possible for sodamide only. Is possible with the sodamide only. Okay. This benzene mechanism is possible with which one in the sense with the sodamide only it is possible. So aryl halides with the sodamide in liquor ammonia goes for benzene mechanism. What is the intermediate in the sense benzene is the intermediate. So now we will take in benzene mechanism another reaction we'll see. Now I will take CF3. Here Cl, like this we have taken. Now we will take this for benzene mechanism. So we have to take NH2 minus. We have taken sodamide in liquor ammonia. First step, what? Elimination, removal of proton. Therefore, NH2 minus has to abstract proton. NH2 minus can abstract which proton? Sir, in previous case we will see. NH2 minus has abstracted which proton in the sense alpha hydrogen. Chlorine is attached to this carbon. This carbon is alpha carbon. So alpha hydrogen is abstracted by NH2 minus. Why NH2 minus abstracting alpha proton but not beta proton, but not gamma proton? Because Cl can show minus I effect. Minus I effect, inductive effect depends on distance. Shorter the distance,